Since the early days of our country, guns have been almost as much a part of the Navy as its ships. And it was only natural that the art and science of naval gunnery would become just as important as the designing and building of ships. In fact, as naval ships came to be primarily regarded as gun platforms, gun requirements increasingly influenced ships' design and size. Thus, as we developed a technology that permitted us to build larger and larger guns, our naval ships also got progressively larger, culminating in the huge, heavily armored dreadnoughts of World War II. Most of these large ships carried 16-inch guns, and some of the Japanese battleships had 18-inch guns. We were also planning to build guns of this size when the interest in guns began to wane. It was the coming of air power that first raised doubts about the effectiveness of naval guns. For with aircraft, the Navy now had to contend with small, fast-moving targets, capable of delivering deadly blows to ships of all sizes, particularly the large ones that had come to be considered practically invulnerable. Not only were the guns heavy, but their fire control systems weren't suited to small, fast-moving targets, and neither was their ammunition. With the effectiveness of air power recognized, a new ship of the line, the aircraft carrier, evolved, which gradually eclipsed the heavy gun battleships and cruisers as the major offensive platform of the Navy. However, carriers were also vulnerable and had to be protected. This job fell to the cruisers and destroyers, yet their guns had a tough time countering aircraft targets. Nevertheless, with developments such as radar fire control and radio proximity fuses, the Navy was still able to effectively combat air attacks with its guns. Actually, the guns were very effective until, with their kamikaze suicidal attacks, the Japanese began using human-guided missiles. When the guns we had were unable to cope with this new threat, the Navy began looking for more effective measures. We knew we had to increase accuracy. The answer seemed to be in some form of steering, such as intelligence, in the projectile itself. The era of the guided weapon was dawning. But at that time, the electronics needed for guiding a bullet could not survive gun launch forces. A gentler initial acceleration was needed. Consequently, attention was focused on guidance of rocket-launched weapons. There were also other considerations undermining the Navy's traditional reliance on guns. The great cost of building, manufacturing, and manning larger ships strained naval budgets, and so we stopped building the larger ships and began retiring those we already had. The remaining ships were left with only 5-inch guns. With gun systems receiving lower and lower priority, many of our newer ships were only able to accommodate 3-inch guns. It was the development of missiles that made possible this downgrading of gun systems. And soon missile launchers were replacing guns on practically all the ships. This reliance on missiles reached a point where ships were being built or refitted with almost no provision for guns. The result was a severe lessening in these ships' defense against a close-in attack on the surface, and making them useless in fire support for amphibious operations or any offensive anti-surface role. The extensive use of our naval guns against shore targets in Vietnam pointed up many of their shortcomings. The performance and reliability was that to be expected of a technology that was now 30 or 40 years old. Many broke down or wore out under continuous use, and their accuracy was poor when compared to target-seeking missiles. With the development of solid-state electronic components, sturdy enough to be fired from a gun, the Navy renewed its interest in its guns and decided to embark on a gun improvement program. The program had 3 objectives. First, update the gun mount. so that its capabilities would be more in line with current naval needs. Second, improve fire control by simplifying the system and giving it greater versatility, accuracy, and reliability. And third, develop a new ammunition with improved safety, effectiveness, and range. The gun system selected for improvement was the 5-inch 54 Mark 42 Mod 7. The improved mount would become known as the Mod 10. To make this conversion, the power drive, hydraulic system, and receiver regulators had to be replaced, and the hydraulic fuse setters had to be improved. The vacuum tube type electronics were replaced with solid-state electronics, and more reliable proximity switches were installed. Operational control of the mount was transferred to a centralized console below deck. And finally, the new mount was given the capability of simulating operations without actually cycling ammunition through it. Improvement of the Mark 68 fire control system called for completely new equipment. For example, the old analog computer was replaced with the Navy's newest digital computer. Not only was it much simpler, smaller, and lighter, but it was much more reliable and efficient. And what's particularly important today, it costs much less to build and maintain. The conical scan radar used in the old fire control system was replaced with a completely new monopulse radar. The new radar not only provided greater accuracy, but also a low altitude acquisition and tracking capability that the old radar never had. This was made possible by incorporating a low target mode that eliminated the usual interference from surface reflection, causing multiple images to be returned. A new electro-optical sensor system was also added to fire control. One part of this sensor system is a thermo-optical receiver, which serves as the eyes of the fire control system. This receiver permits the target to actually be seen on a TV-type screen, either day or night, and at the different command centers on the ship. Another part of the electro-optical sensor system automatically drives the director, so that a line of sight on the target is constantly maintained. The sensor also has a laser system, which can be used for range finding or target illumination. Singly or together, these two laser functions give gunnery an accuracy that was never before possible. The development of new ammunition was prompted by reports from Vietnam of ammunition exploding in gun barrels. The cause of those accidents was improper loading or packing of the explosive charge in the projectile, which the manufacturer was not always able to detect in normal inspections. In order to make inspection of the explosive easier, the new projectile was designed as a two-piece assembly. This made it possible to use an encapsulated charge that could be thoroughly inspected before it was placed in the projectile. The plastic capsule also served as a mold so that the explosive could be cast. And this eliminated a number of hazardous procedures in the loading and assembly of the projectile. By completely separating the explosive from the fuse, another hazard was eliminated. The new design would also accommodate all NATO fuses. A new plastic rotating band replaced the metal one previously used, thus eliminating the need for critical materials, such as copper. And since the band breaks away after leaving the barrel of the gun, the projectile has less drag in flight. This, together with the improved ballistic shape and the use of a more energetic propellant, gave the new ammunition ranges which formerly could only have been attained with rocket assistance. By using new materials and construction, the fragmentation capability of the projectile was increased to give it greater effectiveness. Another important new addition to the system is the velocimeter, which is a low-powered Doppler radar that measures the velocity of the projectile as it leaves the gun barrel. The velocimeter permits gunners to precisely and continuously gauge the performance of both ammunition and guns, and thus increase their accuracy. When we add up all the improvements and innovations produced by the programs, we have an impressive list of gains. Not only is the gun safer, but it's also easier to use and requires a smaller crew. Its operational performance and reliability are much higher. Where the old gun had an expectancy of 135 rounds before failure, the new system will fire an average of 338 rounds without failure. And equally important is the increased effectiveness of the system, with its greater range and accuracy. However, we can't begin to appreciate the importance of these improvements until they're coupled with the great advances made in developing guided projectiles. For only then can we begin to see the vastly increased defensive and offensive capability the Navy can now have in its guns. The development of the guided projectile, coupled with gun improvements, now gives our guns the potential accuracy comparable to guided missiles. One of the principal advantages of guided projectiles is that, unlike their missile counterparts, they don't need complex guidance systems to place them close enough to the target during the critical homing phase of guided flight to be effective. This is particularly true in long-range surface-to-surface operations. This means that guided projectiles are simpler and consequently less susceptible to failure. It also means that they're smaller and require less storage and handling space aboard ship, and that they're also harder to hit with counterfire. With all their advantages, the cost of guided projectiles is only a fraction of that of comparable missiles. However, in spite of the many important advances introduced by the gun improvement program and guided projectile development, they still do not reflect the potential capability of naval gunnery. For technology, which is directly applicable to gun systems, is not standing still. This is particularly true with both the 5-inch 54 caliber Mark 45 and the 8-inch 55 caliber Mark 71. Both of these guns, recently introduced to the fleet, were produced by a technology of the 50s. Our new Mark 45 is smaller and only 1/3 the weight of the Mark 42. But we had to sacrifice almost half the firepower in the Mark 45 to get this reduction. Technology will permit a weight reduction today without a sacrifice in firepower. In addition, fire rates can be varied from much lower rates to much higher rates. The advantage of tailoring the fire rate to that demanded by the threat is deserving of much serious consideration. The range of the 5-inch gun can be extended to as much as 20 miles with low-risk solid propellants, a range previously attainable only with 16-inch guns. The same technology could also produce a lighter 8-inch gun, 35% lighter than our new Mark 71, and capable of firing guided projectiles over 50 nautical miles with pinpoint accuracy. These even newer weapons would require 70% less maintenance and have much greater reliability, with an expectancy of 3,000 rounds of firing before failure, as opposed to 338 rounds for the Mark 42 Mod 10 and 862 for the Mark 45. The savings in installation and checkout time would be even more impressive. The shipyard installation and checkout time for the Mark 42 is 1 year, with 670 hours just to install and connect wiring. A new 5-inch gun could be installed in 24 hours, and wiring connected in just 15 hours. The timely application of advancements in technology to weapons such as these will keep our Navy, the great mobile defensive and striking force, that it has always been, second to none.